Alright, I think we're about to stream. Let's see. Did it show up in here yet? I think so. Let's pop this out. Put this right here. And did it show up in here yet? Can I hear myself? Sound coming through? I think so. Let's pop this out. Yeah, there we go. Alright, I'm gonna post on my story and then let's start. Can do copy this link and let's put this right here. I'm also going to post this in a couple servers. I think I have that open up here. Matrix multiplication, and we'll post it over here. Bam. Alright, let's get started. So, same old setup. Got Triton Puzzles collab. Got this prompt. Also have this other repo open in case there's anything like wrong with it. Some people have notes written about them, about certain puzzles. Looks like this one doesn't have any recorded mistakes, at least not in this repo. I might check the Discord real quick too, actually. Check GPU mode. 'Cause sometimes there's stuff that comes up that makes it hard to solve. Some submission should be able to share the next puzzle 11. For 11, 0 plus block equals block. Is there anything else? I think that's it. Alright, so let's tackle it. Puzzle 11 is matrix multiplication. We have a blocked matrix multiplication. It uses 3 program ID axes. Block size B2 represents the batches to process out of N2. Block size B0 represents the rows of X to process out of N0. Block size B1 represents the columns of Y to process out of N1. The middle shape is mid. CIJK equals sum of, I know how matrix multiplication is defined. You're allowed to use TL dot dot, which computes a smaller map mole. Hint, the main trick is that you can split a map mole into smaller parts. Yeah. And so it uses 3 program ID. Block size B2 represents the batch's process. And so I'm imagining this is supposed to be, this is N0 by N1, and then to multiply them together, they have to have the same dimension here. So this is going to be N1 by N2. And then as a result, we'll get a N0 by N2 result, which is this, right? So, B0 is our rows, B1 is our columns, and that's going to give us like a tile like this. And then B2 represents the batch of the process out of N2. See, that part's confusing me a little bit. Oh no, I get it. This axis is already determined, so we just need one more here to know the tile. Batches process into rows, columns. And since we're using 3 axes, we're not even going to do the accumulation, right? On the, well, we kind of have to, right? What So there's something a little confusing here, right? At this diagram. When we do our result, let's say we're finding this entry right here. We're going to have to do the dot product of these two, and dot product of these two, and then add them together here. But if we're doing them all independently, that means that we might have to, we have like a shared, if we were doing the loops like we were doing earlier with the for loops, then I would just accumulate, right, in here. But if we're using a third axis, right, where it's like, okay, one thread is going to do this, one thread is going to do this, and so on. For like a whole row, they have this as a shared resource. And so I might need to start using locks and stuff. It's actually not clear to me yet if that's what they're asking about. Let's start just writing stuff a little bit though, right? And we'll figure stuff out in due time. X, Y, and Z. So I here is the batch dimension, and then J and K are our matrix dimensions. Is that correct? So I'm going to say row offsets equals TL.A range 0 to B0, and call offsets equals TL.A range 0 to B1. See, what is mid and B mid? B mid isn't even mentioned, right? Row offsets, call offsets. The middle is shape is mid. Let's just print. Let's print a bunch of these, cause I'm not sure I'm seeing it. Yeah, I don't know. Row offsets, call offsets, and then block size B2 represents a batch. It's a process. So let's just call that batch offsets for TL.A range of 0 to B2. And so we should just be able to do something that's kind of similar to regular matrix multiplication, but with these blocks. It's just not clear to me, like, let's make sure that we use the actual PIDs, right? Let's say PID 0 is going to go to the row. Which PID I use matters. For profiling, that is. We want to make sure that we assign the... I'm going to just do it sort of arbitrarily at first, but later we should... Where do the puzzles come from? Bro, just come in. They come from... I think this is one of the people that helped make Triton, actually, but I'm not sure. I know it was like recommended in a lot of the circles I was looking at for like resources and stuff. Person I know for sure works on it, his name is Karen Joe. I might be saying that wrong, right? There's a dude named S Rush on GitHub. The set of puzzles is meant to teach you how to use Triton from first principles in an interactive fashion. But so it's from, it's from this repo. I have this link right here. And it lets you run it without having to pull or whatever. So when we assign these PIDs, the axis matters because it sort of helps inform like the access pattern. But I don't want to think about that yet because I don't even have the algorithm concretely in my head yet. I'm kind of just filling in the gaps a bit, right? So I'm just gonna put them in order that I have it right now. But later we can sort of examine it a bit and see if there's like a more cache friendly axis pattern. Times B2. So this is going to sort of make sure that the block that we're on is corresponding to like whatever PID we're on. Broski. Like if we're on 0, it'll be on block 0, 1 will be on block 1, and so on. It's also, we could do our row, we could do our masks too. So row mask equals row offsets less than n0. We could do the same thing for column and batch, right? Could say column mask is, this is just so that we don't go into a memory that we don't own, right? So like if I have block size 32 and it goes over the edge of my array, I don't want to write past my array. So we're gonna go like that. This looks right. Batch is 4. N2 is 4. Batch is 4 up here. Now I need to actually use my brain though. So I've done the easy stuff. This is sort of just like making the Triton pieces. Now I need to actually think about like, what am I loading? What am I storing? What should I keep in SRAM? What should I not? I think what would make sense is just like pull a chunk out, right, of X and Y, do the product, and then save it to the correct position in Z, and just make sure I'm adding it to that position. So that's the weird thing. In the last one, we did it. My intuition is telling me like, my intuition is telling me to accumulate it, right? Like, I should make a block that has the result of a row and a column, right? Like when I'm thinking about parallelizing a matrix multiplication, I might think about just like a bunch of elements, right? Some way more than this maybe. And the naive thing would be, let's just try doing every row and column in parallel, right? But that's a little too naive, because most matrices are going to be too big. They're not going to have power of 2 sizes. Like if we're trying to do it scaled up. And so then the next less naive thing to do is to sort of split it into blocks. Like you see in this image, I have blocks. Then I can do the rows and columns of blocks independently, and there won't be so many, right? But even in the naive version, what my mind would tell me to do is like, okay, I'm going to do a row and a column independently. What I should do is I should initialize my entry for Z at 0 and accumulate the results inside SRAM. Don't keep looking back and forth at X and Y, and then write. Versus since I'm doing 3 axes here, it seems like I need to keep writing back and forth. That's like a bad pattern. I don't know if there's a way to improve that. Let's just do it poorly first and then see about optimizing later, right? So first thing is just, can we get it working? Let's do X block equals this, and Y block equals this, right? Then we'll say our Z block equals TL dot dot X block and Y block. And then we'll write that Z block, right? So first, how do we get this X block? We need to form our X offsets from our existing offsets. So we need to think about, we're accessing in row major order, right? So we have batch by row by column. So I will add call offsets. We need to have the batch offsets plus the row offsets plus the call offsets. And we need to adjust each of these so that they have the right dimension and then the right starting number, right? So for our rows, we would need to multiply by however many elements are in each row, right? So that would be whatever this is, n0, n1. We want this to be n1. And like, what is this shape? This is going to be a n2 by n0 by n1. So this one should be multiplied by n0 and n1, right? And then we need to do the thing. We need to expand the dimensions. So this one should be, this is gonna confuse the shit out of me. I always get confused. We want this one to be like a column vector. We want it to be, but it's a triplet. We want it to be like this, and this one should be like this, and this one should be like this. I think this is a little bit hard for me to think about, right? TL.load x pointer plus x offsets Honestly, we should probably just put these on this to make things a bit easier. Like that. And then we can have our X mask. We'll say this should be called mask. And we'll say row mask and call mask and batch mask. Like that. Like this. That's our X block loaded out. So this is going to give us like each of our individual elements in an array. This is going to give us each of our rows in row major order. Then this is going to give us our batches in row major order, third dimension. For a Y block, what are we doing? We have row and column. Here we have, what is this? It's inverted, it's like weird. We're still gonna have the same rows. But it's gonna be different. Now each row has n0 and 1. Oh, okay, I'm getting it. Block size B2 represents the batches of process out of N2, which means one of these matrix dimensions is not labeled with an N, right? We have like several matrices that we need to multiply stacked on each other, and the rows of X are N0 and the columns of Y are N1. So this is N1, this is N0, this dimension right here, the middle shape is mid. I get it now. This shape right here is mid because they're the same. So down here, I need to think about this a little bit differently, right? Row mask is this, column mask is this, but mid should be, oh man, this is a little confusing. So instead of N1, this should be mid. This is mid elements. This is mid elements, right? So for each row, we want to start with many elements. And then, so let's look at the shapes. Let's look at the shapes, right? It should be, we have a, what are the dimensions of this? It's going to be the batch. So we have N2, N2 by how many rows is it? It's N0 by mid, and then we're going to multiply that with a another N2, but then this one is going to be mid by N1, right? Yep. And then the result is going to be a N0 by N1. That makes more sense now. So this is N0 by N1 result. So we need to think about this when we're doing our offsets, right? First dimension is mid, so it goes here. Second dimension is N0, so we have N0 times mid. You always just multiply these from right to left. So for this one, we would want, for Y, what we want is row offsets times N1. And then we, well, this is confusing too because it's, oh man, it's like transposed. But the multiplication we're gonna have to do is like this, right? Yeah, like for whatever row we're on here, this is actually determined by mid. I think what I was saying makes more sense now too, right? Okay, so we've parallelized across badges, and then we have a row and a column. So we have this row, say in this column. What I was saying makes sense. We need to initialize a result space in SRAM, and then accumulate across it. And then we could think of that as like that's our mid, right? So what do I want here? That's what B mid is also. At least I think, right? What is B mid when we printed it? 16. Little confused, but we move on. I think I need to be thinking about this a little bit differently. Like, I think it would make sense to say we have a Z block, which is, what should the dimension be? It should be, we could do that right here, right? It should be N2 by N0 by N1. So for our individual thread, it should be B2 by B0 by B1, right? Because that's sort of the pattern that we're doing. So we'll say this should be a TL dot zeros, and the shape should be, am I still recording, Bob? Yeah, there we go. Shape should be B2 by B1 by B0 by B1, like that. Right. And then we're going to say for so I have this row and I have this column, but I need to know how big my chunks should be in here. I think that's what B mid is. B mid, right? But so I'm gonna say for, I don't know what to call this. I'm just call it middle in TL.range, and we're gonna start at 0. Then we're gonna go to, how long should this be, right? This should be mid long. And then we're gonna go by B mid steps. Now I can do my X and my Y chunks, right? And finally what I would do is I would say Z block plus equals this, right? And at the end, so I do all of it in SRAM, I do all of the accumulation, I make this TL.zeros, it never gets written to the high bandwidth memory. When I'm reading my X block and my Y block, I do my matrix multiplication, and then I accumulate it in SRAM here, and I only finally write it to high bandwidth memory back to where PyTorch can access it at the end. So I would say TL dot store Z pointer plus whatever, figure it out later, right? My Z block. And probably my Z mask, which I'll also figure out later. So maybe let's just call this Z offsets. I don't really know. We'll fill those in later, right? I'll say Z mask right here, and Z offsets right here. But so now the question is just how do we get these correct pieces, right? Loaded from our X and Y in our loop. So I think the first thing that we should realize is that because we're thinking of it in this dimension and we have this B mid, we're always going to be loading in every single batch, right? So really the only thing that's going to get adjusted here is the rows and the row and column. I might have to start writing some numbers for this one. I'm having a hard time keeping it all in my head, right? But like, I think I get what I need to do, right? So what I need to remember, I need to keep track of like which rows and which columns I'm really talking about, right? Because these rows and columns, the ones that we've already defined, are sort of telling us which part of X and Y that we're accumulating, right? Like the rows is going to tell us which part of X we're accumulating, columns is going to tell us which part of Y we're accumulating, But what it's not telling us is which columns of x we're looking at, or which rows of y we're looking at, right? And that's going to be determined by our loop here. The middle loop, whatever block we're on, say it's this block, and we need to matrix multiply with this block and add the result in here, right? Wherever we are in our loop is going to inform the column for this sort of global row, and it's going to inform our row for this sort of global column that we're looking at in our individual threads, right? So maybe what I should sort of say is like x column equals this, right? And y row equals something, and these should have something to do with the middle, right? I'm just not sure what yet, like how to actually derive the expression. And then our x offsets would be the batch offsets, which we always have. Plus the row offsets, which we always have, but then this call offsets, it's a different column, right? This should be the x column offsets or whatever, right? Because the other column is referring to the columns of y and not the columns of x. And the same thing for y, right? We want to have a y offsets with the y row with the y row offsets in it, right? Let's see. X offsets equals this. So I don't want to say this is y, like that. Put a y pointer, put y offsets, y mask, and then this should say y row offsets, like that. This mask needs to look a little different too, right? We need to have like a x column mask and a y column mask or whatever, right? And so this might help me actually understand what these need to be, right? This would be a y row mask, sorry. So I know I don't want my y rows to run off the end, so it should never exceed middle. Same thing with this, it should never exceed middle. But I know for sure that this is gonna happen because of this, right? So maybe this should be the thing I'm looking at. Let's see. So I think this x column offsets should just be this middle, right? And for the y row offsets, should it also just be this middle? But it needs to be like a TL.A range 0 to B mid, like that, plus middle. TL.A range 0 to B mid plus middle, right? Like that. I think, right, we're gonna have a little mid-sized block, And this is going to tell us where in our dot product we are, informed by this middle in the loop. The thing I'm having trouble visualizing is the dimensions, right? Like, where is this going, really? Would we say, what would we say? Like, this needs to get expanded a certain way, and I'm not sure what the way is yet. And I do need to rethink these two column offsets, right? So do these need to have the, like, this dimension right here? And this needs to have this dimension right here. If I get this right on the first time, I'm just gonna be nuts. I'm doing so much programming without running anything. Really, I should probably be looking at intermediate values, but I can also just do that when I'm done. Because this right here, this will be call offsets. And then we will add the row offsets here. Like this. No, you're still thinking this wrong. So we have batch, row, and column for X. Batch is shared. Row is determined by our row offsets, and the column offsets are determined by our middle. So this part's right. But for Y, we have batch, row, and column. The batch is global, shared. But for the row, it's going to be determined by the middle and by nothing else. This row offsets is just not relevant at all to Y, right? Y doesn't care what row here we're on, because we do the same thing in this column. So I think it would be like this. This also looks wrong, right? How many elements are there in each row? There are n2 elements. No, n1. n1. So right here, it should be n1 and then mid times n1. Like that. That makes sense. This is symmetrical now, right? n0 mid, mid n1. This mask also needs to look different, right? We need to have the X mask be the batch mask and the row mask and the X column mask. And we need this Y mask to be the batch mask and the Y row mask, and then just the regular column mask. Finally, what are our Z offsets and our Z mask? Z offsets should be n2, n0, and 1. So it's still going to be an expression like this, except this time, how many elements are there in each of these rows? There's n1, right? And then we should actually use the row and column offsets here. This is where we care about both, right? Row in column is this Z block. Row in this column is this C block, so on. So same thing over here. When we do our mask, we're going to use the global ones, right? And then I think we store. This might be correct. I probably mess up the axes somewhere, but I think this is the general algorithm, right? Let's try it out. See what happens. Let me see, one required positional argument D type. Oh, am I zeros? Right? Or where? Yeah, zeros. Let's just make this type 32 for now. Right, flow 32, flow 32. Yeah. So we're gonna say D type equals TL dot flow 32. Try this again. Let's unprint this. Results match true. Correct. Yo, I did the thing. All right. I can't believe I got that right on the first run. My intuition for the axis splitting stuff has gotten a lot better. There's one more thing I want to look at though, right? Which is, did I assign these in the correct order? I'm not 100% sure how to determine that. Let's think about it a little bit since we saw it. What do we want for this axis pattern, right? What are we trying to mitigate? So we already mitigated a bit of back and forth like reads and writes by doing this, right? We put our Z block in SRAM, we accumulated an SRAM, and then we only store after the fact, right? But something that's not so obvious is that when we're doing these loads with the X block and the Y block, there's caching, there are caching operations that we're taking advantage of here that the different, like the streaming multiprocessor will sort of automate for us in the Triton engine, right? So like there's an extra argument here called cache modifier, right? That takes in different string arguments and would force us to always go back, right? So like let's say if I needed a lock to use high bandwidth memory as like a locking mechanism because I have a shared resource. When I load my lock in, I'd want to always go back to high bandwidth memory. I wouldn't want to look at like a local copy that's been pulled into cache that isn't shared across every single warp, right? And so you have the flexibility to change that in Triton. Point is here is that when we load in these X blocks and these Y blocks, if we load them in nice order, we can take advantage of those cache hits, right? Like so what would a good example be? Oh man. Let's get rid of some of these markings. I guess a good example would just be let's number these right. Let's number let's say this is, let's just think about 2 dimensions. Let's not think about batches, right? Let's say this is 0 0 and 0 1 and 1 0 and 1 1. Process 0, if we assign it to this row, like what order would we want to fill these in and load the stuff in, right? Let's say like I load this in. This is going to be used both in this operation and this operation. This is going to be used both in this operation, so on. And this one, this one's going to be used in this operation, but not this operation, right? Not this operation. There's an order that I can load them that will be beneficial. There's a reference I want to look at real quick. Let me look at this real quick. I'll look at that in a sec. There is a file I want to open here. I want to say code dot dot slash let's get this one right. Notice PID 0123. All would read the first row of A. But they all read different columns. Yeah, this indexing scheme right here, right? Basically, what order do we want to do these in, right? Now I know how to say it better, right? It'd make more sense if we made this a little bigger. So let's try that. Let's make this a little bigger like this, and paste these in. Same thing, I'm going to copy this over, delete this one, paste. So I might make it even bigger just to help myself think about it a little bit easier, right? Come on. So these are my two matrices that I'm doing tiled stuff on, right? Tiled matmul, block matmul. If I just assign these in order, right? So if I do 1, 2, 3, 4, that's not a 4. Oh my gosh. 4, 5, 6, 7, 8, and so on. If I do it like this, then these will be saved in cache for each of these columns, right? Each column I go on from, they'll read these same X's, and so we'll get a cache hit there, and that's good. Fewer reads, right? Actually, am I even saying this right? Let me make sure I'm saying this right. I shouldn't be calling them cache hits either, but that's my mental model of it for now. The bad thing is that since if I went through these in this order, right, I'd essentially have to reread in the entirety of my second matrix. And the same thing is true, like if I went in this order, then I'd be getting a bunch of reuses for the columns, but then the rows, I'd be reading in the entirety of my first matrix each time, right? So what would be preferable is if that we also accessed it in a blocked pattern, right? So it would be preferable if we could sort of do like a like a 1, 2, 3, 4, and 5, 6, 7, 8, something to this effect. It doesn't have to be exactly like that. The 5, 6, 7, 8 could be down here, right? But the point is just that if we could kind of read them in this blocked order, then I would use this column twice and this row twice for each of this row and columns versus so I would get 2 reuses, which means only 2 reads each versus 1 read plus 4 reads, right? 1 read that you reuse 4 times and then 4 reads, that's 5 reads versus 2 reads on each matrix that I reuse 2 times each, that's only 4 reads. So I get fewer, right? And you get a better trade-off for different block sizes and stuff. But so the point here is like PID 2, it should belong to the batch, yes. But PID is 0 and 1, there's something here where it's like, I don't want to actually go in order, right? I don't remember how to do this though. I think I gotta do some math. I see what I do. I can just multiply whatever column I'm on by 2, or whatever my block size is, and then I adjust the other side accordingly too, right? So how would I do this properly, like the way I really want? I think this does it automatically. I think over here I was doing it batched, right? Let's see, how many axes am I using here, right? Matmul kernel. This is just one axis. Yeah, that's something to keep in mind, I guess, for if I was doing fewer dimensions, just thinking about the axis pattern. I think I actually did it right this time, right? Because the PID2 is on the batch dimension, which is less important in this case. All right, cool. I think I'm gonna end it there. Pretty happy with that. Oh, one more thing. Let's look at the reference solution here, right? Let's go to puzzle 11 somewhere along here. Makes it a little easier for y'all to read. Softmax kernel, flash attention. These look about right. This looks about right. Yeah, they didn't do anything special with the accessing, and they assigned it just like I did. I to J and K to 0 and 1. Yeah, so I think our solution is exactly the same as the reference. Let's see if it'll run. I kind of doubt it will because it's kind of been breaking, but we'll give it a shot. Let's see if I can run it on my friend's GPU right over here. Let's put in this right here, and let's try running it. I'm going to say source is my virtual environment, and then we're going to run this right here. Yeah, see, I don't know. I think this is just not working properly anymore. This is the 12th, right? Oh no, it is 11. Or is it? I don't know. Let's see that we're not accidentally not running puzzle 11 or something. Yeah, let's uncomment this. Yeah, see, I don't know what's going on with this script, but I'm gonna add my solution so y'all can see it anyway. So I'm gonna say git add puzzles, and we're gonna say git commit dash m matmul, and we're gonna push. And yeah, thanks for watching.